A chain of islands scattered across a deep blue expanse has long been associated with beauty, tourism, and a distant memory of volcanic violence, but beneath that calm surface, a more subtle and persistent force is at work. How stable is the ground beneath one of the most iconic landscapes in the Aegean? How do hidden fractures beneath the seafloor quietly reshape an entire region over time? And why does a pattern of small, frequent earthquakes raise questions far beyond their individual size? Near Santorini, seismic activity has been unfolding in a way that reveals far more than momentary shaking. The region is currently experiencing an earthquake swarm, a clustering of seismic events that occur within a relatively confined area over a limited span of time. While each individual event may appear minor, their collective pattern offers a detailed glimpse into the ongoing processes shaping the Earth's crust beneath the Aegean Sea. The earthquakes are not randomly distributed. Instead, they form a concentrated zone that includes a small island near its center, suggesting that the activity is tied to specific structural features beneath the surface. When this region is examined using satellite imagery or detailed bathymetric maps, the seafloor reveals a network of elongated, dark, linear features. These are not arbitrary markings, but the visible expressions of major fault systems, fractures within the Earth's crust where blocks of rock move relative to one another. These fault lines correspond closely with variations in seafloor depth. Where the crust has dropped, deeper basins form, while elevated sections mark areas where the crust has remained relatively higher. This uneven topography is not static. It is the result of continuous deformation driven by tectonic forces. The crust in this region is under tension, being gradually pulled apart over time. This stretching process creates fractures, and those fractures evolve into active fault lines. Each earthquake represents a small release of accumulated stress. As tectonic forces pull the crust apart, stress builds along these faults. Eventually, the rock can no longer withstand the strain and slips, releasing energy in the form of seismic waves. While a single movement may involve only a few centimeters or inches, repeated events over extended periods contribute to significant geological change. The pattern of earthquakes in this area reflects the geometry of the underlying faults. On seismic maps, the events often align in linear or slightly curved formations, tracing the orientation of these hidden structures. This alignment is not coincidental. It is a direct indication that the earthquakes are occurring along specific fault planes rather than being scattered randomly throughout the crust. This region's geological framework is shaped by a broader tectonic setting that is both complex and dynamic. The Aegean Sea lies within an area where multiple tectonic plates interact. To the south, the African plate is moving northward and being forced beneath the region in a process known as subduction. At the same time, the Anatolian plate is shifting westward, while the larger Eurasian plate provides a relatively stable boundary to the north. These combined movements create a system where the crust is not only compressed in some areas, but stretched in others. In the Aegean region, extension dominates. The crust is being pulled apart, leading to the formation of normal faults, structures where one block of crust drops downward relative to another. Over long periods, this process produces a landscape characterized by alternating basins and ridges. The ongoing earthquake swarm near Santorini is a direct expression of this extensional environment. As the crust continues to stretch, faults are repeatedly activated. Movement along one fault can alter the stress distribution in the surrounding area, potentially triggering additional earthquakes on nearby faults. This interconnected behavior means that seismic activity can propagate through a network of structures, rather than remaining confined to a single location. Another factor influencing the frequency of earthquakes in this region is the presence of fluids deep within the crust. At significant depths, water exists under high temperature and pressure, often mixed with dissolved minerals. These fluids can migrate through fractures and along fault planes. When they do, they reduce friction between rock surfaces, making it easier for faults to slip. This process does not necessarily lead to larger earthquakes, but it can increase the number of smaller ones. The result is a swarm-like pattern where numerous low-magnitude events occur in rapid succession. The presence of fluids effectively lubricates the faults, allowing them to move more frequently than they might otherwise. The sea floor surrounding Santorini provides additional evidence of this active environment. Its rugged appearance, marked by steep slopes, abrupt changes in depth and irregular formations, indicates a history of repeated faulting and deformation. These features are not relics of a distant past. They continue to evolve as tectonic forces remain active. One of the key concerns associated with this type of seismic activity is the potential for a larger event. While most earthquakes in a swarm are relatively small, they indicate that stress is being redistributed within the crust. In some cases, this redistribution can lead to the activation of a larger fault segment, resulting in a more significant earthquake. Even a moderate shift along the seafloor can have broader implications. A displacement of just a few meters, equivalent to several feet, may seem minor on a planetary scale, but it can be enough to disturb the overlying water column. When this happens, energy is transferred into the water, generating waves that can travel across considerable distances. Historical records in the region illustrate this possibility. A major earthquake in the Aegean during the mid-20th century, with a magnitude exceeding 7, produced a tsunami that affected multiple coastal areas. The event likely involved not only fault movement, but also an underwater landslide, a process where unstable sediment on steep slopes collapses and shifts rapidly. The presence of steep underwater terrain near Santorini increases the likelihood of such occurrences. As faults move and reshape the seafloor, they can create conditions where sediment accumulates in unstable configurations. A sufficiently strong earthquake, or even a series of smaller ones, can trigger these accumulations to fail, leading to sudden displacement. The relationship between fault activity and seafloor morphology is central to understanding why this region requires close observation. The same processes that create visually striking underwater landscapes also contribute to potential hazards. Each earthquake, regardless of size, is part of a larger system that continuously modifies the structure of the crust. The alignment of seismic activity also highlights the importance of mapping and monitoring fault systems. By tracking where earthquakes occur and how they cluster, it becomes possible to infer the location and orientation of faults that may not be directly visible. This information is critical for assessing how stress is distributed across the region and how it may evolve over time. The persistence of the current earthquake swarm suggests that the underlying processes driving it remain active. Rather than a brief burst of activity, the pattern indicates a sustained period of adjustment within the crust. This does not necessarily imply that a major event is imminent, but it does confirm that the system is undergoing continuous change. At a broader scale, the Aegean region serves as an example of how tectonic forces operate over both short and long timescales. Individual earthquakes occur in seconds, yet they are part of processes that unfold over thousands or even millions of years. The stretching of the crust, the formation of faults, and the gradual reshaping of the seafloor all contribute to an evolving geological landscape. Near Santorini, this evolution is particularly evident. The combination of extensional tectonics, active faulting, fluid migration, and complex plate interactions creates a setting where seismic activity is both frequent and informative. Each event adds another piece to the overall picture, revealing how the crust is responding to the forces acting upon it. The significance of these observations extends beyond the immediate area. Similar processes occur in other regions, where the crust is under tension, making the Aegean a valuable natural laboratory for understanding how faults behave in extensional environments. The patterns observed here can inform studies of seismic activity elsewhere, providing insights into how and why earthquakes occur. As the swarm continues, attention remains focused on how the sequence develops. Changes in the distribution, frequency, or magnitude of earthquakes can offer clues about shifts in the underlying system. These variations may indicate adjustments in stress, alterations in fluid movement, or interactions between different fault segments. The interplay between these factors underscores the complexity of the region. Fault lines are not isolated features. They are components of an interconnected network influenced by both mechanical forces and the movement of fluids. Understanding this network requires careful observation and analysis, as well as an appreciation of how multiple processes operate simultaneously. Beneath the tranquil waters surrounding Santorini, the Earth's crust is far from still. It is being stretched, fractured, and reshaped in ways that are only partially visible from the surface. The ongoing earthquake swarm is not an isolated phenomenon, but a manifestation of deeper forces that continue to influence the region. And as these subtle shifts accumulate, they raise an enduring question: how do these countless small movements occurring far below the surface combine to shape events that can be felt across entire coastlines? The answer lies in the continued motion of the faults themselves and in the evolving balance of forces that govern one of the most geologically active regions in the Mediterranean. The continued sequence of earthquakes in the waters surrounding Santorini does not exist in isolation. Each tremor, regardless of magnitude, is part of a broader and interconnected system in which stress, structure, and movement interact continuously beneath the surface. What makes this region particularly significant is not simply the presence of faults, but the way those faults behave under persistent tectonic stretching and how that behavior can evolve over time. Within the Aegean Sea, the crust is undergoing extension, meaning it is being gradually pulled apart. This type of tectonic setting produces a distinct style of faulting, where blocks of crust move downward relative to their neighbors. Over time, this creates a fragmented structure composed of alternating elevated ridges and subsiding basins. These basins, often filled with layers of sediment, can appear stable on the surface, while concealing ongoing deformation below. As stress accumulates within this stretched crust, it does not distribute evenly. Certain fault segments may remain locked for extended periods, resisting movement even as surrounding areas experience frequent smaller earthquakes. These locked sections are capable of storing significant amounts of energy. When they eventually release that energy, the resulting earthquake can be considerably larger than the events typically observed within a swarm. This uneven release of stress is one of the reasons why fault systems near Santorini require careful attention. The presence of frequent smaller earthquakes does not necessarily reduce the likelihood of a larger one. In some cases, these smaller events can transfer stress to adjacent fault segments, increasing the potential for a more substantial rupture elsewhere within the network. The geometry of the faults also plays a crucial role in determining how seismic energy is released. Many of the faults in this region are not simple straight lines. Instead, they consist of interconnected segments that bend, branch, and intersect at various angles. These irregularities can act as barriers that temporarily halt the propagation of a rupture or as points where stress becomes concentrated. When a rupture encounters such a complex structure, its behavior can change rapidly. It may slow down, stop, or jump to an adjacent fault segment. This ability to transfer movement between faults increases the complexity of the system and introduces additional uncertainty into how earthquakes may unfold. Beneath the seafloor, the presence of accumulated sediment adds another layer of complexity. Over time, material eroded from nearby landmasses settles into the basins created by faulting. These sediments can vary in thickness and composition, and under certain conditions they may become unstable. When shaken by seismic activity, they can shift abruptly, triggering underwater landslides. Such landslides are capable of displacing large volumes of water, even in the absence of a major fault rupture. The steep slopes that characterize parts of the seafloor near Santorini make these events more likely, particularly when combined with ongoing seismic activity. The result is a secondary hazard that exists alongside the earthquakes themselves. The interaction between fault movement and sediment stability highlights the importance of viewing the region as a system rather than a collection of isolated features. Each component, faults, sediments, fluids, and tectonic forces, contributes to the overall behavior of the area. Changes in one part of the system can influence conditions elsewhere, sometimes in ways that are not immediately apparent. Fluid movement within the crust remains a key factor in this interaction. As previously noted, high-pressure fluids can migrate along fault planes, reducing friction and allowing for more frequent slip events. However, this process is not uniform. Variations in temperature, pressure, and rock permeability can influence how fluids move and where they accumulate. In some areas, fluids may become trapped, leading to localized increases in pressure. When that pressure reaches a critical level, it can trigger a sudden release in the form of an earthquake. This mechanism adds another dimension to the seismic activity, one that is not solely dependent on tectonic stress, but also on the dynamic behavior of fluids deep underground. The continuation of the earthquake swarm suggests that these processes are actively ongoing. Rather than a single cause, the pattern reflects a combination of factors working together. Tectonic extension continues to pull the crust apart, faults respond by slipping intermittently, and fluids facilitate that movement by reducing resistance along fracture surfaces. Over longer timescales, this continuous activity contributes to measurable changes in the structure of the crust. Basins may deepen as fault blocks subside, while adjacent regions remain elevated. These differences in elevation influence not only the shape of the seafloor, but also the distribution of sediment and the pathways through which fluids can move. The relationship between these processes becomes particularly important when considering the potential for larger events. A significant earthquake in this region would not simply be the result of stress accumulation along a single fault. It would likely involve the interaction of multiple elements, including the geometry of the fault network, the presence of fluids, and the stability of surrounding material. Historical patterns within the broader region provide context for this possibility. The Aegean has experienced earthquakes that have produced both ground shaking and secondary effects, such as tsunamis. These events demonstrate that even moderate changes in the sea floor can have consequences that extend far beyond the immediate area. A displacement of several meters, or a few yards, along a fault may be sufficient to disturb the water above it. When this displacement occurs rapidly, it transfers energy into the ocean, generating waves that can travel across significant distances. The impact of such waves depends on a variety of factors, including seafloor topography and coastal geometry. Underwater landslides can amplify this effect. When sediment collapses and moves downslope, it can displace water in a manner similar to a fault movement, sometimes producing waves that are disproportionately large relative to the initial trigger. The steep and irregular terrain near Santorini creates conditions where such events are possible, particularly during periods of heightened seismic activity. The ongoing swarm also raises questions about how stress is being redistributed within the crust. As faults slip, they relieve stress in one area while potentially increasing it in another. This redistribution does not follow a simple pattern. It is influenced by the orientation and connectivity of the fault network. In some cases, this process can lead to a gradual migration of seismic activity across a region. Earthquakes may begin in one location and then shift along a chain of faults over time. Tracking these movements provides valuable insight into how the system is evolving and where future activity may occur. Monitoring efforts in the region rely on the analysis of seismic data, which records the timing, location, and magnitude of earthquakes. By examining these parameters, it becomes possible to identify trends and patterns that might otherwise go unnoticed. For example, changes in the depth of earthquakes can indicate variations in the conditions within the crust, such as the movement of fluids or the activation of different fault layers. The depth distribution of earthquakes near Santorini suggests that activity is occurring within a defined range beneath the surface, consistent with the presence of active fault structures. This concentration supports the interpretation that the swarm is primarily tectonic in nature, rather than being driven by volcanic processes alone. At the same time, the region's volcanic history cannot be entirely separated from its tectonic behavior. The processes that formed Santorini are closely linked to the movement of tectonic plates and the presence of magma beneath the surface. While the current swarm appears to be dominated by fault activity, the underlying geological setting remains complex and interconnected. This complexity is part of what makes the region both scientifically significant and potentially hazardous. The same forces that create dramatic landscapes and attract visitors from around the world also contribute to ongoing geological change. Understanding these forces requires continuous observation and careful interpretation of subtle signals within the data. If you found this breakdown helpful and want more clear explanations of complex Earth processes, make sure to like, share, and subscribe. And do not forget to tap that hype icon to help this reach a wider audience.